Okay, last part, and also a correction to the previous one because I'm not redoing it. The correction first, where I put the Lyapunov function here, this obviously is all of these terms squared, so it goes from 1 over 2 gamma to 1 over gamma, and similarly here, that's those terms inside the bracket both squared. So there we go, quick correction made there. Right, neural network, adaptive neural network control is used. I've written the assumptions here. We have a system with unstructured uncertainties, so there are uncertainties that change and are a function of the state. So here, state is x, and our uncertainties are this minus f of x being a function that changes, is dependent on x. We can't just design an adaptive controller for this because it first of all changes, so it's not constant. So our adaptive law falls apart. But also we don't know, it's unknown, so we don't know f of x, so we really don't know this function. But we can use a neural network to basically approximate this function as a combination of other so-called basis functions, and the basis functions are going to be denoted by h of x, and these are standard basis functions. There's various standard basis functions you can use. So I'm just going to call it h of x. And what we do to solve this problem, this is a first order problem obviously, is we basically say our unknown function f of x is equal to a constant set of weights. So this is a vector, a column vector perhaps, of weights multiplied by our basis vectors. And now what this lets us do is it lets us rewrite our x dot as minus w, and remember this is a column vector, so transpose to multiply it by the basis vectors, wt h of x plus u, like that. And now we can design our controller, approximate controller u hat. I'm going to skip a few stages here, use feedback linearization. Well, we need it to be w h of x, and then we add in our terms for feedback linearization for a first order system, minus x d dot, that is, like so, and then our controller gain k0 e, that's our controller. But remember u hat, we don't actually know w, so it's not w, it's w hat, like that. Cool. Substitute that controller back in and we will get x dot is equal to same thing as the previous two parts. We define m tilde here as m minus m hat in the same way that we define w tilde as w minus w hat. So I guess I should do tilde w. And if we look, if w tilde is w minus w hat, we have minus w plus w hat, so it's minus w tilde, transpose h of x, our basis functions, and then minus x d dot minus k0 e. Now we define our error dynamics. E equals x minus xd. Take the first derivative. This is how we did it for the first order system with adaptive. E dot. Okay, it's doing some weird thing. This doesn't seem to work, so I'm just going to get rid of that block. E dot is equal to x dot minus xd dot. and we have x dot already, so we can substitute in these dynamics. E dot is equal to minus, and we've already substituted, so this is basically this x dot here, we've already substituted in our u, so I'm just going to copy these because it saves me some time. Like so, and then minus xd dot, oh yeah, a note here, actually I've made a mistake, it's plus xd. That is how I do it in the feedback linearization lesson, so hopefully that's fine. Plus xd, because what happens is now we have minus xd dot, and then this one here is plus from our controller, and they just cancel each other out. And that leaves us with, what I'm going to do is I'm just going to cancel them out from here, get rid of them, basically. That leaves us, E dot is this. Great, let's define our Lyapunov function. 1 over 2 E squared, because we want to basically get E dot. And then we do our classic adaptive parts, 1 over 2 gamma. I need to bracket those correctly. 1 over 2 gamma multiplied by our unknown, which in this case is W tilde transpose, and this will be squared, but with a vector, or in this, a matrix or whatever it might be, to square this, we just multiply it by itself, tilde W, like so, but the non-transposed version, right? We understand why this would work. Two matrices multiplied by each other, one transposed and one not, will be the square of that matrix. Cool. So now we can define V dot as E dot plus 1 over gamma and it's going to be W tilde transpose, nothing changes there, and the next one will be W tilde dot, which is good because we'll recognize that that will be our adaptive control law in a minute. First thing we want to do is substitute in our E dot, so it's going to be E multiplied by, well, let's have a look what E dot was, here it is, substitute that in there, and this second part is unchanged for now. Cool, and now let's take out some terms that we want to keep and group up some other terms. So E times minus K0E is minus K0E squared, and this is ultimately what we want V dot to be equal to, but we've got to consider our W tilde. So remember how we did it before, add W tilde and then group the terms. So the positive W tilde is in terms of just W tilde dot and 1 over gamma. Like so, and the negative is just actually what I should do here, because I missed this, that is obviously transpose, because we've got W tilde transpose and W tilde transpose. Here it is h of x, and don't forget e, we multiplied it by e when we expanded this bracket, so hxe, and that's that done. Now we use that same notation that we used before, where we say the W tilde is W minus W hat. So W tilde dot, starts getting a lot of things, is equal to W dot minus w hat dot, and remember w is a constant. I mean, it's a vector, column vector, but they're all constants. So the first derivative is 0. So we can say that w tilde dot is equal to minus w tilde hat dot. Sorry, w hat dot, like that. So now w hat dot is our adaptive law. This is something we can choose. So we need to look at a w hat dot in this equation. It's over here. And what do we need to make it equal to cancel out this bracket altogether? Well, it needs to be equal to our basis vectors, our basis functions, h of x, well, sorry, gamma, 1 over gamma, let's get rid of that, times our basis function is h of x, e, but remember, it is w hat dot is equal to minus w tilde dot, and this is w tilde dot here, so we just need to conserve that sign and put in a minus there. So that is our adaptive law for the neural network, and that would leave us with the final dynamics, final Lyapunov function of minus k0 e squared. Great, that's what we wanted. So that works, and we can then obviously go on to prove stability with Lyapunov stability analysis and see that it's negative definite, and obviously we can control k0 so we can ensure that that is always the case. It's very, very similar to adaptive control. You just have to basically make that first step, which is to change this unstructured uncertainty, this function of x, into a combination of some constant weights that we are basically is now our unknown constant in our adaptive controller, multiplied by some basis vectors which basically never change. There's some basis functions. So yeah, that's how we do it. And this is still a function of x, but the point is, because we are only choosing w, we can cancel out those dynamics later in the game by designing an appropriate adaptive law, and it gives us a v dot that is nice. So I believe that's everything. Hopefully this video gets watched so you understand, so I can correct my mistakes from previous lessons where I missed out that squared. But I mean, even if you miss it out, most of the logic is still pretty sound. Yeah, so that's it. I'm going to stop this recording now and upload the videos.